All right, folks, let's get started. Cool. I'm going to introduce myself because I'm probably the most appropriate person to introduce myself since I know myself fairly well. Some of you that I know many of you, but some of you I don't. My name is Patrick. I'm faculty here. I've been with the RLAI since around 2009, though really first started bumping into the RL part of the university about 2004. So this talk is going to give you a bit of context on something that, in fact, Rich and I have been thinking on quite hard for a really long time, and that's the topic of intelligence amplification. The way we might begin to extend our own cognitive powers. And this isn't going to solve that problem for you. And Rich, I mean, we're actively working hard. We were just, Katya, who's the floating head at the front, Rich and I were just talking about this even 15 minutes ago. So I'm not going to help to solve that, but I am going to hope to give you a little bit of a window into the role predictions might play in some of the core problems. That's my goal for the day. I just want to lay that out in front. It's also a debugging talk for a talk that I will give next week at the International Conference on Rehab Robotics. I finished this talk at 12:30 a.m. yesterday, so if there's bugs in it, I apologize, but not too much. So let's get started.
Which you'll be happy to hear about. So
yeah, this is going to be great. Okay, cool. Actually, no. Okay, sorry. Can you help me move this? This is right in the way. I'm going to bump into it. Thank you. Let's go this way. Is here maybe over here at the back?
This is part of the talk, by the way. We rehearsed this.
Did we? Sure. Yeah. Let's dump it here. That's fine. Let's just dump it there. All right. Cool. All right. So. What you probably think, if those of you who know me, I've worked on mostly robotics forever. I usually take reinforcement learning algorithms and I throw them into robotic settings and see where they break. So when I give you a talk, we're probably thinking joint action. This is Gautam Vasan, one of our old students, who's now with Kindred. And we worked a lot on robots together. Many of my students and I worked on robotics. And so you're probably thinking, or maybe you thought when you saw my talk title, that I was going to talk to you about the action or actuation of joints. If so, I'm sorry to say that you would be completely wrong. I'm in fact going to talk to you about exactly what you and I just did, which is in fact joint action. So this is the topic of my talk. And I hope you'll actually see how we might get back to joint actuation from joint action. But really, I'm going to be doing what you see. This is a picture from a paper by Pesquita et al. That came out last year. But we're going to be using this canonical example of joint action, which is moving a table together, which you and I just elegantly demonstrated for you a few seconds earlier. Actually, a better example was us trying to leverage this darn thing from outside of the closet, which was really hard. Okay, cool. So I do want to walk into what joint action is so that we're all on the same page. Because this is probably not going to be a talk full of algorithms. In fact, I can promise you, I think, no math and no wiggly lines. So this is Sabans et al. Natalie Sabans back in 2006 sort of wrapped up a field that has now become known as joint action out of a lot of literature on human-human interaction, bodies and minds moving together. And so Natalie Sabans and others defined this as joint action as a social interaction where you have two or more individuals and they're working together, they're coordinating their actions in both space and time to bring about change in the environment. Okay, so when I talk about joint action today, yes, joint actuation as well, but for now, please humor in and let's work with this definition. And so for the interest of today, I did want to unpack what people see as the key components of joint action. And for now, let me still say that I'm talking about human-human joint action. Think of tango dancers or you and I moving a table, which is much less elegant than tango dancers. And so several people have started to unpack this. One was Vesper and colleagues in 2010, but the definition of the components I'm going to use comes from Anna Pesquita and Whitwell and Jim Enns from UBC. And really, it starts with three parts. And so the first part of joint action in the mind of Pesquita, again, building on what Natalie Sabans and others have said, is that it revolves around the representation of a shared goal. Okay, so I highlighted two words for you here because those of us that care about RL will care about both those words. And the individual contributions, again, multiple agents interacting to that shared goal. A second piece of this, and this is also something that I think many of us here will care about, is the monitoring and prediction of a partner's actions. So I just highlighted again some of the words that are probably very familiar to us, which is monitoring, think of it as sensation or observation, and prediction. And the third part of the definition of joint action and its components is, in fact, the continuous coordination via, and again, I highlighted important words, the continuous improvement of predictions about a partner's actions. Yeah, Rich?
Would a better word than continuous be continual?
It probably would. I'm actually using the words from Mesquita et al.'s paper.
You mean continual as in time?
Absolutely. So I agree. I totally agree with you. I would say in the flavor of continual learning that if I were to remap the words from the paper, I'd say continual coordination via the continual improvement of predictions. It might also be continuous, but in this case, it is the smoothness in time. Okay, so joint action. Social coordination to achieve some kind of change in the environment, and we do so via representing a goal, by monitoring and predicting another, and by adapting our predictions about that other. Everyone tracking? Cool? Okay, I'm going to take a fast pace today to keep myself awake. Again, 12:30 a.m. I stopped doing this. So let's talk a bit about predictions, because I think many people here are probably experts in predictions. Whether computational or biological, I think you're all probably pretty good at it. If not, your cerebellum sure are. And the first case I'd like to bring out is the kind of predictions that we see quite commonly, and that's a momentary kind of prediction. It's a instantaneous classification, a nice mapping of a label to some kind of true outcome or some kind of ground truth. So there's a momentary kind of prediction, and in the kind of work that I do, and many of the folks that are here from the Blink Lab who work with people interacting with machine learning systems for rehabilitation. Ahmed, who's sitting right there, is a leading expert in some of the forms of machine classification and regression. That this is used quite commonly, the idea that you might map some kind of observation space to an immediate label or classification. There's another kind of prediction. There's plenty of ways we can think about predictions, but there's another that I think many of us here also think about, and that's the temporally extended kind of predictions. Maybe not like what's the right class label right now, but how is the future going to unfold? And one way to think of this might be something like an expected return, a summation of a signal into the future. Because all of artificial intelligence clearly started around 2010, we can ignore Rich's 1988 paper, which said we could predict arbitrary signals and their returns. And I'll point out the Horde paper here, where we sort of generalized prediction learning, and especially temporally extended prediction learning of different kinds of signals at different timescales. Okay, so for now, let's set aside our differences and say you can have these different kinds of predictions, and in fact that they could be acquired or updated either in large batches, offline is an extreme case of this, or we might be able to acquire and update these kind of predictions during a stream of ongoing experience. Cool? Okay, awesome. So I'll jump back into the human world a little bit and use one of the figures from, I think, one of my favorite papers. And this is a paper by Daniel Wolpert and Flanagan and others. It's required reading for anyone who really joins my team. It's called Perspectives and Problems in Motor Learning. And Wolpert and colleagues use these awesome Calvin and Hobbes cartoons. There's also a lot of really good work by folks like Flanagan et al., other authors, and some other really neat work in the human brain that thinks about how our brains use predictions. Ahmed is also saying they really, I know how brains use predictions. I think you do, so is Ewan. And what's cool about this is that you could say that not only does the brain use predictions, and there's some evidence that in fact the acquisition of predictions precedes the acquisition of control by biological learning systems, that in fact the feeling like we're even moving, the feeling that that I have agency over my emotions or that I performed an action may in fact stem from our brain's prediction of the motor outcomes and not actually the sensory feedback from that action. A couple tea time talks ago, Adam Parker talked to you very briefly about forward and reverse copies, and that fits into that story. So brains, all sorts of brains, biological brains, use predictions, and in some cases even base their feelings of agency, it's thought, on the predictions and not actually the control actions. Okay? So let's step back into human-human action, not just the action of a single individual, but let's assume there are two humans interacting. A lot of folks have thought very hard on this, and one team that has is, again, Daniel Wolpert, but also folks like Doya and Kawato, and they propose something called the Mosaic Model. It's quite complex, and I don't really want you to dive into the detail of it, so I'm just going to highlight a few things here, is that the model that they have for motor control during social interaction, the way that two individuals will forecast the way that the other is moving and their movement intentions, it is all about the prediction of different controllers, the outputs of those controllers, the consequences of those control actions, and the error in those particular predictions. So this is the way that folks like Wolpert and Doya have thought about using predictions as a fundamental element of coordination, social coordination between two agents that are working together to complete a task. Okay? The next example is much more recent. I mentioned that the paper by Anna Pesquita and colleagues. And in this case, they have something called the Predictive Joint Action Model, or PJAM, which is a cool title. And again, they are talking about predictions. Here, they're again looking at joint action, the way that people coordinate. This is a great paper. If you want a quick summary of what people are thinking in terms of joint action, I highly recommend this paper. And again, they base their, remember back to how we define the fundamental elements of joint action. They base their PJAM model on things like the prediction of sensory observations, the prediction of motor states, and the prediction of some joint or coordinated represented state of the two or more interacting agents in this particular setting. So can they build it on predictions? And cool, so we're just like, oh yeah, there's human stuff, that's great. And another point is that this isn't all about just human interaction. Okay, at least a couple people are chuckling, I'm not the only. Okay, great. All right, cool. So folks, I really like some of the work by Giovanni Pezzulo. He's got an excellent body of work. And one particular paper I wanted to call out is this one, where they were looking at joint action between a human and a computer agent. This was in more of a human-computer interface sense, but the human and the computational agent were performing joint action, building up forecasts of each other to play this little stacking game. Some other work I'd like to call it, it's actually really recent. It's some work we've done here at U of A in DeepMind on immersing people in virtual reality in a virtual reality foraging task, and then having a prediction learning agent begin to build up predictions about the person build up predictions about the agent, and then learn communication and control policies in this foraging space. And of course, video games is another great example. We have, pick your favorite subset of games where you have a digital agent that jointly acts with you to achieve your objectives in the game. Navi's one example. Okay, is everyone on track still? I think we're going at a good pace, because I'm going to jump into what Rich and I have really unfolded as communicative capital. Is everyone good so far? Did I step over something that you want unpacked right now, or? Okay, cool. Let's keep the pace. So what's nice about all of this, from the perspective of someone who, with Rich, wrote a paper on this, is in fact that maybe we can start to think about predictions as especially in joint action, as this fundamental unit of capital that two systems acquire as they work together. Rich and I were just talking about this with Katya even, that sometimes you have to invest in the future. You have to sacrifice short-term gains to be able to build up some kind of infrastructure to do your job down the road. And so one thing we've thought about, and we write this out with a few of our colleagues here, students from here at the University of Alberta. We wrote up a nice paper. It's about 33 pages long, but it's a good read, I promise, where we start to unpack this idea that predictions actually are one of the elements that two agents will begin to sculpt and cultivate, to refine as they interact. And that not only does this prediction learning ability begin to define the maximum capacity that this partnership could have in completing objectives, but that in fact the acquisition of predictions, the maintaining and updating, and the early accrual of predictions is in fact helping to realize some of that full capacity. That by the time two people are working together, if you and I were working really well together to move this table, we'd have darn good predictions of how each other are going to move, how our body language cues. We'd have great predictive models of each other, and probably think of each other as agents with some kind of shared goal, but also individual components of that shared goal. So predictions are a great part of this. There's also the goal-seeking aspect, but I really would like to decouple that from today's talk, because then we'd be here for an hour and not just 20 plus minutes. Okay, so I'm going to dive into some of the examples then, some of the ways that people have actually started to look at humans and machines jointly acting without calling it that. So this is one that I think a few people in the room will be familiar with. Sometimes people with amputations will wear a prosthetic limb. It's a robotic device. It's attached to their residual limb, and some of the more advanced or more modern upper limb prostheses will in fact monitor signals from the human body. They'll monitor via electrodes, and they will make classification-based predictions based on the signals that are being recorded from the human body. Person flexes their muscles in one way, and that system thinks, okay, I better close the hand. Person flexes another way, the hand opens, or maybe the wrist rotates if they're very lucky and have really advanced technology, or maybe their elbow moves. This is, again, I'd like to say that this is not too simple an example to be considered a form of joint action that is in fact involving prediction learning. The person is almost certainly learning motor predictions about how this robotic device will behave, and the system itself is also learning predictions about the person. In this case, it's often done in batches of training or in short training episodes, but the system is acquiring predictions about the person, and in some of the newer systems, being able to update and maintain those predictions in intervals over the course of use. Here at the University of Alberta specifically, we've looked at more continual forms and continuing and persistent forms of prediction learning. So in this case, really early on, we started this work in about 2010, and we finally published a paper on the core idea back in 2013. We looked at building architectures of temporal difference learners, in this case, general value functions, to predict a whole range of aspects about the interactions between a person and a robotic rehabilitation device, specifically a robotic limb. We built up architectures wherein a system could, without any training intervals, so I'm showcasing one example of the real-time aspects, where a system could begin to build up forecasts about the outcomes in terms of human biosignals or in terms of the interactions that their robot arm might have with the world. We build up those in real time, online, and through ongoing experience. So we showcased an architecture for doing this, preliminary data, and then proceeded for, well, okay, so I've done really like one thing for the last almost 10 years, which is to throw general value functions at different signals from human-robot interaction in the rehabilitation setting. And so we kept doing that. We looked at people with amputations and without amputations, people who, like this individual here, had targeted muscle reinnervation, where their nervous system has in fact been rewired to better interact with robotic devices. And so we studied all the ways that we could begin to make forecasts, long-term, temporally extended forecasts about the signals flowing from and between a person and their assistive device. And a setting that you could, again, very reasonably begin to call, as we move forward, joint action. And also, joint action. Good, thank you for hearing me with chuckles. Okay, cool. So the natural question that comes after this is, well, sure, you can make lots of predictions. Well, your predictions are great. What do you do with those predictions? And so I'll tell you one thing that you might do with the predictions. And in fact, Ann Edwards had what I think is actually a really elegant thesis. She graduated back in 2016, but she had a really wonderful thesis on using learned predictions, general value function style predictions, for those who are familiar with generalized value functions, to govern the way that a person might switch between many different modes or functions of an assistive technology. This is a really cool setting. The person is learning about their device, they're using their device. As they use their device, the device begins to actually build up predictions about what they're going to do and when they're going to do it. And then when it's really sure about that, it begins to actually do some of those things for the person. That was like the culmination of Ann's thesis. It's nice. Both systems are building up, maintaining, adapting predictions of each other as they pursue the task that has been, in this case, set out by the person. That's not all. So Adam Parker is presenting a paper actually next week at ICOR on a different view into this. These are all views, by the way, on something that we've called, and Adam and Rich and Joseph Model especially called out as Pavlovian control, the hardwired mapping of predictions to control. Not policy learning in any of the senses we usually think. It's a nice hardwired mapping of learned predictions to specific control outcomes. Adam's been using this work in a different way in terms of mapping learned predictions learned by a robotic device, in this case, say, worn on his body or worn by someone else, mapping those predictions back to feedback, the way that the system communicates in this case, in terms of vibrational motors, back to a person as they navigate through a physical workspace to help them streamline their interactions. So this is neat. Like we say, we can make predictions in real time in an ongoing sense, and then these are just two of the many examples of how we've started to integrate those into the way a person interacts with their device. And so I'm going to start to come home with one final theme of arguments here, is that really we now have something that's really special and that we haven't had before. We finally have both the technology and in fact the model human-machine systems to study human-machine coordination, especially human prosthesis coordination, as joint action. This is something we never had before. And I'm going to say, really, it's more like this, is that we now have viable real-time machine learning and human-machine interaction to study this. And of course, because I'm a one-trick pony, what I really mean is that we have generalized value functions. I kind of know how to use them sort of most of the time, and I can stuff them together with people in an interactive setting and pursue my curiosity about joint action. So it's not just that. We've gotten to the point, this is a great photo by Amber Bracken at the Canadian Press during one of the photo shoots recently, and that we also have the ability to change those model systems. So we can fabricate new robotic arms, we can change them as we see fit, we can use inexpensive technologies to record from the human body and in some senses the human mind. We have computation technology that lets us do experiments in real time and adapt them in real time while people are interacting with technologies. And as a shout out to Dylan, who's presenting his paper next week at ICOR as well, in certain settings where we have interaction between human and an adaptive device, in this case Dylan's auto-leveling wrist, we now also have something that we've carved out through, well, I guess 5 years of grueling labor for those who've been working on the Gamma project. So like you and there and Ida and others that have been working on our gaze and movement assessment suite, we now have the ability to very precisely record how humans move and look, and now hopefully, even if your work goes really well, think, to actually study the interactions between humans and their devices. And so this is it. I'm gonna close with this, is that right now, we have a setting that's pretty special, and we really didn't have before in an appreciable or useful sense, is that we have a setting where both humans and machines can now represent goals, can make and maintain predictions. It doesn't mean that those are fancy predictions or that they have a perfect representation of goals, but we now have a setting where we can actually try to study joint action. We can actually put together a person and a machine and study how they adapt predictions about each other, how they represent their parts of a shared goal, and how they update and maintain those predictions to pursue that goal. So now we can ask this question. And it's the question I really, really care about, and it's the only thing I'm probably going to do for the next 5 years with all of my hats on, is to figure out, can we actually gain some utility by viewing human prosthesis interaction as joint action with those conditions that I set out earlier? And I'm going to say, let's find out. This is our big thing. So now I'm going to wrap up. Lots of people have worked on a lot of the pieces that I've talked about today. Lots of different labs and teams have all come together, especially the students and trainees who've worked with us over the years, and especially Rich, we've thought about this for, again, almost a decade together. So it's a big challenge, but I think, if you don't actually care, that's okay. Check back in with me in 5 years, and hopefully I'll have something new to show you in 5 years. All right, thanks so much, folks. How's the time?
2016. 20 minutes and 16.
Yeah. It's because I talk fast. Any questions?
Well, just a quick one. We now have the ability to maintain and something else predictions.
Yep.
In real time.
In real time. Yeah.
I think that's important.
Yeah. It's lots of words on a slide, but duly noted. I'll try to cut some other words. I was trying to minimize slide word count. But yes, in real time, this is huge. I mean, I do want to dwell on this in a second, because this is, if you look at sort of the titles of the papers that Rich and I wrote for, I don't know, the period of like 2010 till maybe 2016, almost everyone had real-time machine learning in some way in the title or the abstract, because it was something different and special. It was something that people were not focusing on, especially in the rehabilitation setting. And I think we can almost declare victory here, is that, at least in the rehab setting, due to our action or not, people are now starting to appreciate that systems need to be able to machine learn in real time, in one way or another, to actually fulfill the needs of people using technology. So I think that's a cool win, and I do want to celebrate that. Martin.
Yeah, what is a shared goal? And is it really so that two people have a shared goal in the sense of having a common goal? I can think of a demonstration with your table there, where I have a goal, you will be able to help me, but you never know that goal until the end.
Yeah. So when I said I want to explore this problem fully, this is actually one of the things I think is really important. It's something that I know a few of us have talked about, is one way you could think about a shared goal is actually very crisp, which is to say that both systems actually share a reward function. That the reward going to both, obviously human sensory motor processing, something, I don't know, evolution, that the way I perceive reward as points or whatever isn't going to actually maybe map directly to changes in my dopamine or something. But we could say, like the example paper I showed you in VR, we actually had one of the settings there was the person and the system actually both receive the same reward. In this case, the machine receives the same reward that the person is acquiring through their interactions. That's one choice. It's not the only choice. We could imagine that we have to assume some kind of modeling of the other goal and the alignment of those goals without them being predefined. I don't know what the right answer is. And yeah, please.
Simple idea that I have the goal of moving the table someplace. I can realize that with you helping you without you ever knowing where that goal is. In some sense, I could implement a simple agent on you that simply maintain the pose of the table a bit,
Mhm.
up above
Yeah.
the table and follows me, right?
Yep.
I mean, isn't it so that many of the things we're talking about could be, if we look into human interaction, it would be very difficult to distinguish exactly if it gets fully shared or not, right?
Oh yeah, like the paper that I showed, the Anna Pesquitas paper that had the picture of the two kids moving the table out for a garden party. I mean, one of the kids might be like, "Don't make mom mad, don't make mom mad," and the other kid might be like, "If I put this table down, I get cake." Like it may actually not matter at all that the goals are aligned, but as long as they can infer a goal and model the other agent's contribution towards that goal, that might be enough. I don't know. This maybe doesn't have to be defined in a crisp way, and it might be enough to have one agent's goal is in fact to maintain the height and the stability of that particular table. And as long as the person can model that agent as having that goal, then the shared goal itself, or the joint goal, can be thought of as something that doesn't have to be explicitly represented by either agent. This gets to the representation question, which is why I'm sort of waffling in my answer, is that it's unclear what form that representation should take. And a lot of people in literature argue about this for humans and humans, and when we add a machine in the mix that has a different substrate, I think the argument's just going to get deeper, which is why we should contribute to that argument. I don't know the answer. Yeah.
I have a question on behalf of Katya. What do you think about gaining utility by considering human-computer dialogues as joint actions?
I don't see why that wouldn't be joint action. So, I mean, often, so I will say that often we think, or often people phrase joint action as, I'm just going to go here so Kat can actually see me. People often think of joint action as requiring joint action, like moving of the joints, moving of the body. Some people frame this entirely in terms of something that I'm actually fascinated by, which is the notion of peripersonal space, the area around the body on which you can act and interact. So a lot of people will focus the argument in that particular area, but if you look at the way that people talk about this, and in fact the way that other people will discuss joint action, communication actions are almost certainly actions. In Adam's work that he's presenting in ICOR, there's no doubt in my mind that, like, if an agent is taking a communicative action, that's still an action, and those two systems are working together to perhaps perform some kind of shared objective. The work that you're doing in particular, Katja, is very apropos to that. So I don't see that there's any reason why we should exclude that from the definition of joint action, because I think it fulfills, that's why I was saying I have some great references for you. I think some of these actually fit very nicely into the story that you've been crafting. Okay, good, thumbs up. Alex.
So we have real-time learning methods.
Yeah.
We have domains that are interesting.
Mm-hmm.
But there seems to be a large disparity between the examples that are used in a lot of the models of interpersonal or inter-machine communication and what we actually have.
Mm-hmm.
So a number of the examples shown are very much low level, and so the modeling of people is also very low level in comparison to the examples given, like the abstract examples given. So what is required to get from A to B, or why haven't we gotten from A to B in that setting?
So if I think about A as being short time scale, let's say physical, peripersonal, sensory motor interaction, I don't think we understand that well enough to move forward. So that's one gap, is that I think we haven't camped there. Like, honestly, no one's camped there. Like, this is actually that last pitch there, that we can actually study human-computer joint action in reasonable settings, human-machine in general sense, interaction in joint action. This has only just become possible, and so it's actually this like gaping black hole in the literature that we need to start filling. And some of those sensory motor interactions are the in my mind the easiest low-hanging fruit because of the skill set that we have actually in this room. The second piece is that I think to move to more complex interactions, our learning systems have to step up their game. And so, of course, I just want to use like on-policy general value functions with no fanciness, probably a linear representation. And for as long as I can, if I'm lucky, I can keep doing this until I retire. I probably won't be, and I'll have to use a deep net someday. But either way, like, my feeling is that there are, like, if we move into different styles of problem, we're going to have to up our game in terms of the way that our algorithms are structured. You're working on some of this in particular, like how we might begin to actually think about crafting an elegant structure of knowledge such that a system could actually really predict how another system might move, might be able to maintain those predictions. So I think that's important. I think that's another gap. And the third is that maybe we still don't understand the human-human interactions as well as we can, or even just the human environment interactions. Now I'm sort of like eyeing you in here, and that there's a lot of room to go in terms of understanding how humans form predictions about their environment, and neuroscience and human behavioral studies haven't solved that yet either. So there's a lot of little pieces. I'm choosing to camp on the first bit, but I think there's a lot of work to be done all across the gulf between A and B. That's my feeling, but I could be wrong. More questions, or are we out of time? Ooh, yeah, Martha. Hi, Martha.
I just want to follow up on Katya's question then about joint action. Because I think this is an example of the joint action setting. So is the joint action setting mainly the cooperative multi-agent setting with two agents? Or is there something different about it than that?
It's I'll drop back to Natalie Sabanza's definition, because I like that one. I can make all my own definitions. Rich and I have tried a couple over the years. That you have two agents that are socially interacting, I take very loosely. So that's the piece of that definition I relax. But two agents interacting to coordinate their actions over space and time to affect change in their environment. And so I also relax the two agents and to say n agents. I actually personally don't know if I'm one agent or lots and lots of agents. I probably think I'm lots of agents. And so in that case, I'm not worried about the number of agents, or even that the agents sort of think of themselves as agents. I want to decouple that as well. But I do like that definition, because it really is about the coordination of actions in space and time to change an environment. And I think with that, we can be that's a very broad definition. And I'm being very broad about it. I'm sure I could go talk to Jim Enns or someone at UBC who'd be like, you're stepping a little bit too far with your way that I'm interpreting that definition. But for the kind of work that I think we're doing here, I like to sort of relax that definition in terms of how I interpret the different words. Is that good enough? Or
Yeah. And so is that, because I don't know anything about cooperative multi-agent setting, is that a cooperative multi-agent setting?
Does it have to be cooperative?
Wasn't it they're jointly trying to achieve?
It's interesting. I've never thought about the question of whether you could not have a I've always thought of it as cooperative. Yeah. So I've always thought of it cooperative because of they can represent a shared goal. But based on Martin's awesome question, maybe there is actually some way that they could not represent each other's goals effectively and still be working together. So anyway, let's say yes for cooperative. I think of it as a cooperative setting. If you think about coordinating actions in space and time to affect change in the environment, that may be framed in a competitive sense too, but I haven't thought about that. I don't know, so I don't want to unfold that one a bit. But I think cooperative. That's my. I like people. I think things working together to make the world a better place. More of the sum of the parts.
Requirement of the shared goal makes it a bit vague. Because for example, if two teams are playing against each other, then does it mean they're adversarial because each wants to win, or are they cooperative because they want to they want to entertain the audience? Yeah.
Yeah. I think yeah.
Is this a joint action between two sports people?
You could think of it as such, and you could think of it as a competitive setting. This is the same problem when we draw agent-environment boundaries. It's the same problem when we try to think about whether your brain is actually a single agent, or if we get sever your corpus callosum, if you would actually have two independent decision-making processes that interact and cooperate. I think it's a hard thing, and we have to make, maybe I'm poorly paraphrasing Rich, is that we have to make choices. And those choices are important, but we should be very clear about the choices that we actually make, because they're going to help us unpack the problem a bit better. And Rich, you can tell me if I'm totally misrepresenting your words.
Well, I'm going to tell you that was very good. Thank you very much.
Thank you, everyone. Great questions.